today we will be considering another algorithm which finds the shortest path between pairs of nodes in the graph. The algorithm for this task, which we covered the last time, was the Dijkstra algorithm. But the Dijkstra algorithm basically computed the shortest path to the source node from other nodes, right? From other nodes, it computed the shortest path to the source node, right? But what if we want to find the shortest path from every node to every other node, right? So for such kind of problem, the algorithm which is used is the Dijkstra algorithm, and this problem is known as all pairs shortest path algorithm. Now, in the all pair shortest path algorithm, the adjacency matrix which I have told you about is changed a bit. If you see here, we have 5 vertices, and these vertices are connected with each other using directed edges. Now the change here is, if you see, vertex number 1 is connected with vertex number 2, it is connected with vertex number 4, right, and it is also connected with vertex number 5. If you see here, vertex number 2, vertex number 4 and vertex number 5, and vertex number 1 is not connected with vertex number 3. So instead of placing a 0 here, which we usually do in an adjacency matrix, here for the adjacency matrix of the Floyd algorithm, we place an infinity here, right? So this is the first difference in the adjacency matrix which we will be using for the Floyd algorithm. Rest of the adjacency matrix is same. Now, how does a Floyd algorithm work? Okay, actually this is the crux of the working of the Floyd algorithm, and I will need a figure to explain it to you. For example, in a graph we have three nodes, right, and this node is connected with this one, and this one is connected with this one, and this one is connected with this one, right? And let us connect these as well. And okay, for example, this node number is 1, this node is, let's say, 2, and this node is 3, and this node is obviously 4, right? Now what we will do, we will pick node number, and let me draw the adjacency matrix here as well. 1, 2, 3 and 4, right? 1, 2, 3 and 4, 1, 2, 3 and 4. Now 1 is connected with 2. Okay, distance, I forgot about the distance. For example, here the distance is, let's say, 3. Here the distance is, let's say, 2. For example, here the distance is, let's say, 20, and for example here the distance or the on the edge is, let's say, 80, right? Now if you see here, this 1 is obviously not connected with 1, although it's the same node, so we'll be putting infinity. 1 is connected with 2 with a distance of 3, 1 is connected with 3 with the distance of 80, right, and 1 is not directly connected with 4, so here we will have infinity, right? Now in this particular, I will be dry running this algorithm over an example graph, but what I wanted to explain here is we will be taking a sample one node at a time. For example, for example, let us take the node number 1, right? And what we will do, we will place this node number 1 between all other nodes, right? For example, rather, let me, if you allow, let me, instead of taking 1, let us take 2 as a sample node. And what we will do, we will put this 2 between every adjacent node. For example, from between 1 and 2, if you go from 1 and 2, we cannot put 2 here in between because 2 is already in between, is on one side. For example, between 1 and 3 and between 1 and 4, in the middle we can put 2, right? So if we, for example, now if I see the adjacency matrix here, now distance between 1 and 2 is 3, right? That is okay. Distance between 1 and 3 is 80, right? Now what I will do, I will pick this 2, and what we will do, we will first go from 1 to 2, and then from 2 we will go to 3. Now if you see here, from 1 to, if we from 1 we go to 2, we reach here using this via through a distance of 3, and then we go from 2 to 3, we reach there on a distance of 2. So if we see, overall we have covered this distance, overall distance 3 plus 2, which is 5. And if you see here, this 5 is less than 80. So what we will do, we will replace this 80 with what? With 5, right? Because the direct distance is much more as compared to the indirect distance, which goes through 2. Then we will try to see if this 1, if we place 2 between 1 and 4, and then we see if whether there is a path from 1 we go to 2, that we can do, but from 2 there is no direct path to 4. So in that particular case, this distance will not change, right? So this is how this algorithm works. So this equation basically demonstrates that in a generic form, that any distance between node I and j, what we do, we take the minimum. For example, whatever the distance, direct distance is between node I and j, and the indirect distance, like from I we do go to k, and from k then we go to j. And among these two distances, whichever is the minimum distance, that is placed here, which I showed you earlier, right? So this is the total concept of the Floyd algorithm, and this is the pseudocode of the Floyd algorithm. Now if you see here, this is the distance matrix, or basically this is the adjacency matrix with a bit of a change, that instead of having zeros showing no connection, we are placing infinity here, right? Okay, and then these, if you see this line number 4 and line number 5, this is basically a for loop, two for loops to traverse a 2D matrix, which will be the adjacency matrix in this case. And this K is important. This basically does what? This picks one node at a time and tries to fit it between every two nodes, and then it will pick the second node and it will try to put it between every pair of node, then it will pick third node, so on and so forth. And here if you see line number 6, here it basically, this line number 6 is this equation. It says that if the direct distance between I and j is greater than the sum of the distance between from I to k and from k to j, then you simply replace this thing. You replace this distance with this new distance, right? So this is the pseudocode of the algorithm, but here one of the information is missing. We know here when it runs, the algorithm runs, maybe we get an updated matrix here. For example, this distance become 4, for example this distance may become 1, and for example this distance may become 5. But by looking at this matrix, we will not be able to know that how through which node this distance become 4 instead of 5, right? So we will be making another matrix as well, right? that will be an empty matrix initially, it won't have any values, but in case we change this value to 4, we will have to put the information of the node as well. For example, maybe for example, if you see here, this is a good example here. A direct distance between V1 and V5 is 5, but if we go from V1 to 4 and then V4 to V5, this distance become 4 by chance. So what we will do, will in the distance matrix we will write the distance, but here we will write the node number through which this distance is achieved, right? So we will be able to not only know the cost, but we will be able to know the route through which this cost is achieved. Right. Now so this pseudocode gets an addition of an extra matrix. This I have explained it to you here, which is actually set to, this is called matrix P, basically the path matrix. So there is not a big change. You see the path matrix is initialized to 0. The rest of the code remains the same, only this last line gets added just in case if we are updating distance I and j, then in the path matrix we keep track of the k as well on the same cell. So that makes us that enables us to keep track of the path as well. Now let us dry run this this concept on this particular example. Now if we see here, this graph contains 3 nodes. Initially this graph represents this adjacency matrix represents the same graph. For example, if you see from node 1 you can go to node 2 at a distance of 4. You see here, now from node 1 you can go to node 2 at a distance of 4, and from node 1 you can go to 3 as well at a distance of 5. That is fine. For example, from node number 2 we cannot go to node number 3 directly, right? If you see here, there is no direct path between 2 and 3, so here we have got an infinity, right? And if you see here, this path matrix is initially set to 0. Now what we will do, we will pick node number 1, and then we will try to place this node number 1 between every adjacent pair of nodes. Let's see here. Node 1 in this cell, if you see, node 1 cannot be placed in between because it's 1 on both sides. In this cell as well, on one side we have 1, and since on one side we have 1, we cannot consider it here as well. Then again between 1 and 3, 1 cannot be considered because 1 is already on one end of the edge. That cannot happen. So for this this cell, if you see, although 2 is on one edge, one side of the edge, but on the other side there is again 2, this cannot be considered. And again this is from 2 on to 2, this cannot be considered. But here if you see, on one side we have 2 and on other side we have 3. Now what we will do, we will try to go from 2 to 1 first, and then from 1 we will see if we can go to 3. Now if you see here, from 2 we can go to 1, right, and from 1 we can go to 3. That's perfectly fine. So the sum is 2 plus 5, which is 7. So what we will do, we will remove it from here and we will put 7 here. Since this 7 is achieved through the node number 1 in the path matrix, in the same cell, instead of 0 we will replace it with 1, right? And then we will go on to the next cell, and if you see here, 3 is on one side, but again on the other side it's 1, so we are not going to change it. Yes, this can be done. If you see here, 3 and 2. Now from 3 let's try to go to 1 first, because we have picked 1 to be placed between all adjacent all pair of nodes. Now if you see here, from 3 we cannot go to from 3 we cannot go to 1. If you see here, there is no path, there is no path. You can see it from the matrix as well. So again that cannot be entertained here, and again 3 comma 3 is sort of the same node, so that cannot. If you see here, we have achieved this, we have achieved this efficiency, right? We have got a shorter path. Now we are done with considering node number 1 between every every pair of node. Now this loop, if you see here, this k value will run for 1, 2 and 3. So for 1 we have done. Now we will do it for k is equal to 2. Now this is the result of what I mentioned earlier. Now let's, rather doing it here, let us do it here. For example, we have considered node number 1 between every pair of nodes. Now we will consider 2 between every pair of nodes. Now we will start from the updated matrix. This was the original matrix. Now this is the updated matrix. So we will be using the updated matrix, not the original matrix, because this way we can have better paths. Now if you see, we are considering 2 between every pair of nodes. So between 1 and 1 it cannot be considered. Between 1 and 2, 2 is already on one side, so we cannot do that. Yes, between 1 and 3 that can happen. Let's try to go from 1 to 2 first. From 1 we go to 2, that is happening, and then from 2 we go to 3. But from 2, if you see, there is no direct path. This is a directed edge, right? So this got skipped. Then this complete row will be skipped for this node number 2, because 2 is already on one side, so this will be skipped. Basically loop will iterate, but it is going to make no effect on the distance matrix. Now considering 2 between node number 3 and 1, if we go to node number 3, and the direct distance, if we see here, is infinity, but let's go from 3 to 2. Yes, we can do that. And from 2 we go to 1, that can happen. So from 3 to 2 we reach there in -3. So -3 plus 2 will be -1, right? So this will get updated, this will become -1, and this path matrix will have a value of 2 here, right? And then this cell will be ignored, because there is a 2 on one side, and then this is 3 comma 3, it won't make any effect, right? So now we have considered 1 between every pair of nodes. We have also considered 2 between every pair of nodes. Let's see if the result is the same. Now in the next iteration, if you see, the result is the same, right? I think I missed, if I'm not very wrong, I missed this point, maybe due to an error or what, or maybe I've not. Let me recall. Let me recall. Wait a second. No, I have not. Right. Okay, fine. Sorry for that. So we are perfectly fine on on right track. Now since we have considered 1 between every 2 pair of nodes, and we have also considered 2 between every 2 pair of nodes. Now using this updated matrix, now we will consider 3 to be placed between every pair of nodes, right? So we'll start right from here. So between 1 comma 1, all actually these diagonal values, all of these will be ignored. Now for this particular cell, between 1 and 2, let's try to go from 1 to 3 first. From 1 to 3 that can happen, and from 3 to 2 we can go as well. So if we see here 5, and this is -3, so 5 plus -3 will be 2. So this is getting decreased by using node number 3 here, right? So this will be updated. Now between 1 and 3, 3 cannot come, because 3 is already on one side. Then between 2 and 1, yes, we can try that. From 2, let's go to 3 first, but if you see here, there is no path, so it won't make any difference. Similarly, this we already skipped, and between 2 to 3, 3 is already one side, this will get ignored. And for this complete row, since 3 is already on one side, so it will get ignored. right? So this is the next update. Let's see if in the actual answer 2 should be here and 3 should be here. If you see the next iteration, 2 is here and 3 here is here. Now this is how the Floyd algorithm works. Now the final output of the Floyd algorithm for this particular graph will be this one, and if you see here, using this this graph and this path matrix, there are if you see here, this is the new path, this is the new path, this is the new path. Rather, instead of watching at these new paths, you simply consider both of these. You see here, if you see here, this distance, these 3 distances have been achieved. They have been decreased. They were actually much more in the original graph, but they have been decreased using the Floyd algorithm, right? So this is how this Floyd algorithm works, and this is the simple pseudocode of printing out this 2D array. You can do it in a much better way using one single for loop. This is a recursive version of the code. So I hope you've enjoyed understanding the Floyd algorithm, and again this works very well. And if you see here, this is a very efficient algorithm. If you see here, all of this algorithm works in order of n cross n cross n, right? Bracketing order of n cross n, which is basically n cube. So this is quite efficient algorithm, right? Okay, I hope this was useful for you. Thank you.